Okay, hello students, welcome to our second lesson in sequencing, and we're looking at applications of arithmetic sequences. So today we want to display the terms of an arithmetic sequence both in tabular and graphical form, and demonstrate that the arithmetic sequences can be used to model linear growth and decay in discrete situations. Now I'm going to particularly use this with financial maths, so we're going to look at particularly depreciation and simple interest. So you may come across things like this on the internet. So if we have a look here at a 52-week money challenge, you can see that if you just, week one, you put in $1, you've got $1 in your bank account. Week two, you put in $2. So you've got 1 plus 2, so you've got $3 in your bank account. Week 3, you've put in 3, week 4 you put in 4, week 5 you put in 5, and so on. You can see that by the end of a year, so 52 weeks, you're just putting in $1 extra each week. You've saved a total of $1,378. Thinking of holidays, I think we've all attempted this napping challenge, and that's worth a little giggle, and you can see that's also a sequence there. We're going to look at two sorts of sequences today, and we're going to look at simple interest and depreciation. So simple interest is calculated as a percentage of the original amount deposited, and the customer receives the same amount of interest at each time interval. Now you're used to I equals PIN down here, and you would have done this last year with me. And what we want to have a look at now is how do we express this as a recursion formula or as an arithmetic sequence. So what we want to first of all work out is the amount deposited each year. And we just say, well, the amount deposited each year is the same as that interest rate over 100 multiplied by the original amount. Now you can see that instead of saying T1, I've written A0. So in this case, I'm saying A for the amount and a 0 for a 0 amount of time. So we're actually putting in money before we're starting to interest. And remember, interest is only earned after 1 year. So that's why I've put in a 0 instead of a 1. And I've put in A for an amount rather than a time or a term. Now, AN is going to be the total amount, and N is going to be the number of time periods. So if we have a look at a tabular form of an arithmetic sequence here, we've got $500 in a bank, and we can see that each year we're just putting in $20. And so what's happening is that we're just going up at a straight or a flat rate here. And so sometimes we'll call simple interest flat interest, because it's at a flat rate. If we were to graph it, the line would be flat. So let's have a go at a couple of equations and problems using simple interest. Using this formula, so determine the amount of the account balance at the end of the term for the following investment. So we've got a deposit of $15,000, an interest rate of 4.6%, and a term of 8 years. So what do we need to do first? We need to calculate the deposit or the amount for each year. Now this is the common difference. So this is the interest deposited into the account each year. So D is still D, similar to your previous formula, and N is still N, but we've just changed it up a little bit. But first of all, let's have a look at this. So we'll calculate the interest amount for 1 year. So we know that, what do we got? 4.6% of the original amount is going to be $690 deposited per year into the account. And we're going to do this for 8 years. So we just got to think about how we express that, and we use that using this formula here now. So to determine the total amount after 8 years, so we say what the total amount is the original amount plus the number of time periods multiplied by that interest deposited each year. So we're just saying $15,000 plus 8 times $690. So that's $20,500. So we just say that the account balance after 8 years is $20,500. Of course, you'll also have to be asked a couple of the other variables, and the obvious one to go for is the time. So that's the number of periods. So let's have a look at this one. So the previous example, but we'll just change it up a little. The length of time required for the following investment to reach $25,000. So we had $15,000, the original amount, interest rate, remember that's this one here, and the term is 8 years. So just as before, we've got $690 going in each year, but we just need to rearrange the equation or transpose that equation to solve for n. So what we've done here is I've just substituted in the values, but you can see that n is unknown. I can then just rearrange or transpose to solve for it. So what do we say? 25,000 take 15,000 is $10,000. That leaves us with 10,000, the same as saying n times $690. And then if I just go that $10,000 divided by $690, that'll give me 14.49 time periods. When we interpret that, we just say that the account balance will reach $25,000 after 15 years. Now, the linear decay is just the opposite. So instead of a positive, we have a negative. So instead of that positive, there's our negative there. So this is a good example of this is depreciation. So it's just reducing at a flat rate. Now, the important thing to note is tax deductions can be claimed for a decline in value. That decline in value is called depreciation. It can be claimed for equipment used in earning an income. So it's very important in business and your own personal life. If you're earning an income, you want to reduce the amount you get taxed by. And so you use depreciation and claim that as a tax deduction. So this has 3 different names. It's called straight line or unit cost or flat rate depreciation. And it's just depreciation claimed as a percentage of the original value. So in this case, instead of using A's or T's, I've used V for value in this case. So Vn is the value after n number of years. VO or V0 is the original value at 0 time. So I'm using this instead of T1. You can see that I've got T1 here. I'm just using VO. And then what else do we need to notice? D, the interest deposited, or that's your common difference each year, or interest depreciated each year. And N is the number of time periods. So you can see that straight line depreciation does indeed appear as a straight line. It's also a flat line. It's also known as unit cost depreciation. So let's give an example. So we want to determine the value of a depreciated item. This time it's a computer bought for $2,000, a flat rate of 12.5% after 3 years. So let's find the depreciation for each year. So calculate the depreciation for each year. So we're just saying, well, I over 100, so what's our I? That's it there. We can express that as a decimal as 0.125, or we can express it as a percentage as 12.5 over 100. And then, so we just say I over 100 times the original value. What's the original value? Is $2,000. So we just say 12.5 over 100 times 2,000. So we have 250 depreciated each year. So to calculate the depreciation after 3 years, we just get the original value and minus the number of time periods, which was 3 years, multiplied by the amount depreciated each year. So it's 2,000 take 250, so 2,000 take 750, that'll give you 1,250. So the value of the computer is 1,250 after 3 years. Now, another important business concept is that idea of when an item has declined so much in value, it's said to be worthless. So you write that off, and you can claim that all as a deduction. So a computer was bought, grammar Mr. Beasley, for $2,000, depreciated with a flat rate of 12.5% after 3 years. When the computer has a value of $300, it's said to be worthless and can be written off. So determine the length of time it takes for the computer to be written off. So as before, we just calculate the depreciation for 1 year, and that was $250. And as our second example in simple interest, we just need to solve for n because we're looking at the length of time. So we just say the value after n number of years is that original value minus the number of time periods multiplied by the depreciation for each year. So what I've done here is just substituted in $300. That's when the value after that number of years, and that number of years is unknown. Here's our original value, and then we know that the amount depreciated each year is $250. Now you can solve this a couple of different ways. Hopefully I don't confuse you with the negatives here. So what I've said is 300 take 2,000 is 1,700. And that's going to be, we'll be left with negative 1,700 is like saying negative n times $250. Now I've divided both sides by negative $250. So 1,700 divided by 250 is 6.8. Negative 1,700 divided by negative 250 is 6.8 as well. So n equals 6.8. So the number of time periods is 6.8. So the computer can be written off after 7 years. So we have displayed the arithmetic sequence in tabular and graphical form, and we can use that to model linear growth and decay, particularly with simple interest and depreciation here. When you've done that, can I get you to work on the mastery exercises, please?